For decades, astronomers believed a supermassive black hole controls the center of the Milky Way. Sagittarius A star, 4 million times the mass of the Sun, was discovered through decades of observations. In 2020, 3 astronomers won the Nobel Prize in Physics for proving its existence. In 2022, the Event Horizon Telescope captured its shadow. Published February 5, 2026 in monthly notices of the Royal Astronomical Society, a team now proposes that Sagittarius A star might not be a black hole at all. Right now, stars near the galactic center orbit at speeds exceeding 2,000 kilometers per second. They complete orbits in as little as 16 years, circling within a region only light hours across. Those velocities should require a supermassive black hole. But astronomers from Argentina, Italy, and Brazil argue that a dense clump of fermionic dark matter can produce the exact same gravitational effects. The dark matter core would be so compact and massive that it mimics a black hole perfectly, and it explains both the violent motion of stars near the center and the gentle rotation of the entire galaxy. The data comes from 3 independent sources. First, precise tracking of S-stars orbiting the galactic center over more than 30 years. Second, observations of dust-enshrouded objects called G sources, which also orbit close to the center. Third, the latest rotation curve data from the European Space Agency's Gaia DR3 mission, which mapped how stars and gas move in the Milky Way's outer halo with unprecedented precision. Together, these observations reveal a pattern that fits the fermionic dark matter model as well as the black hole model. Dr. Valentina Crespi from the Institute of Astrophysics La Plata, lead author of the study, stated, "This is a pivotal point. Our model not only explains the orbits of stars and the galaxy's rotation, but is also consistent with the famous black hole shadow image. The dense dark matter core can mimic the shadow because it bends light so strongly, creating a central darkness surrounded by a bright ring. Still more striking, the fermionic dark matter hypothesis provides a unified explanation for phenomena at vastly different scales. The dense core, only light hours across, governs S-stars. The diffuse halo, extending thousands of light years, shapes the galaxy's overall rotation. In the black hole model, these are separate entities, a supermassive black hole at the center and a dark matter halo surrounding the galaxy. In the fermionic model, they are 2 manifestations of the same continuous dark matter structure. Here is what should concern you most. If the galactic center is dominated by dark matter instead of a black hole, then our understanding of galaxy formation, supermassive black hole growth, and the role of dark matter in shaping galactic nuclei will need to be revised. Sagittarius A star is one of the best studied objects in astrophysics. Thousands of papers have analyzed its properties. The 2020 Nobel Prize was awarded for proving it exists, and now, a team is proposing that it might not be a black hole at all. Think about that. Before we explain how astronomers are challenging one of the most fundamental assumptions about the Milky Way's center, if you want to stay updated on discoveries that question established science and reveal alternative explanations for cosmic phenomena, hit subscribe and turn on notifications. Because what we are about to reveal will change how you think about the galactic center, dark matter, and the nature of the most massive objects in the universe. Leave a comment telling us, did you know that the galactic center might not contain a black hole? Let's start with what Sagittarius A star is. Sagittarius A star, abbreviated Sgr A star, is a compact radio source located at the center of the Milky Way galaxy. It was first detected in 1974 using radio telescopes. Early observations revealed an extremely compact and bright radio emission, consistent with a massive object in the galactic nucleus. Over the following decades, astronomers tracked the orbits of stars near Sgr A star, measuring their positions and velocities with increasing precision. The breakthrough came from 2 groups working independently. Reinhard Genzel's team at the Max Planck Institute for Extraterrestrial Physics in Germany, and Andrea Ghez's team at UCLA in the United States. Both groups used large telescopes equipped with adaptive optics to track individual stars orbiting Sgr A star over many years. The most famous of these stars is S2, also known as S02, which completes an elliptical orbit around Sgr A star every 16 years. S2's orbit is extraordinary. At its closest approach to Sgr A star, called periaps or periastron, S2 comes within 17 light hours of the galactic center. That is roughly the distance from the Sun to Uranus. At that point, S2 is traveling at approximately 7,750 kilometers per second, about 2.5% of the speed of light. The orbit is highly elliptical, with an eccentricity of approximately 0.88, meaning the distance from Sgr A star varies by more than a factor of 10 over the course of the orbit. By measuring S2's orbit precisely, Genzel and Ghez calculated the mass of the object S2 is orbiting. The result? Approximately 4 million solar masses, confined to a region smaller than the orbit of Mercury. That mass concentration is so extreme that the only known object capable of producing it is a supermassive black hole. No other astrophysical object can be that massive and that compact without collapsing into a black hole. S2 is not the only star with an extreme orbit. Astronomers have now cataloged more than 40 S-stars orbiting Sgr A star. S62, also known as S0 102, has an even shorter orbital period than S2, approximately 9.9 years. At its closest approach, S62 comes within 16 light hours of Sgr A star and reaches a velocity of approximately 6.7% of the speed of light, over 20,000 kilometers per second. That makes S62 one of the fastest moving stars ever observed. Another remarkable star is S4714, which holds the record for the shortest known orbital period around Sgr A star, approximately 12 years. But S4714's orbit is even more eccentric than S2's, with an eccentricity above 0.985. At periaps, S4714 approaches within approximately 12.6 astronomical units of Sgr A star, closer than the orbit of Saturn around the Sun. At that distance, the gravitational acceleration is so strong that relativistic effects become measurable. S4714's velocity at periaps exceeds 8% of the speed of light. The S-stars provide multiple independent measurements of the central mass. Each star's orbit depends on the mass it is orbiting and the distance from the center. By combining data from dozens of S-stars, astronomers have determined that the central mass is 4.15 million solar masses, with an uncertainty of only a few percent. The compactness is equally well constrained. All SE stars orbit within a region smaller than 1,000 astronomical units. For comparison, that is roughly 25 times the distance from the Sun to Pluto. A mass of 4 million solar masses confined to that small region cannot be anything other than a black hole or an exotic, ultra-dense object like a fermionic dark matter core. In 2020, Reinhard Genzel and Andrea Ghez were awarded the Nobel Prize in Physics, shared with Roger Penrose, for their discovery of the supermassive compact object at the galactic center. The Nobel Committee cited their work as proof that Sgr A star is a supermassive black hole. But the mysteries don't stop there. In 2022, the Event Horizon Telescope collaboration released an image of Sgr A star. The image shows a bright ring of light surrounding a dark central region, exactly as predicted by general relativity for a black hole. The dark region is the shadow of the black hole, created because light emitted near the event horizon is either captured by the black hole or bent into highly curved paths. The bright ring is emission from hot gas orbiting just outside the event horizon. The EHT image was hailed as the strongest direct evidence for a black hole at the galactic center. Combined with the orbital dynamics of S2 and other S-stars, it seemed to settle the question. Sgr A star is a supermassive black hole, but not everyone is convinced. The new study published in monthly notices of the Royal Astronomical Society proposes an alternative, a supermassive compact object composed of self-gravitating fermionic dark matter. What is fermionic dark matter? Fermions are a class of subatomic particles that obey the Pauli exclusion principle, which states that no two identical fermions can occupy the same quantum state simultaneously. Electrons, protons, neutrons, and neutrinos are all fermions. In the context of dark matter, fermionic dark matter refers to hypothetical dark matter particles that behave like fermions, as opposed to bosonic dark matter, which would behave like bosons, such as photons, or hypothetical axions. Fermionic dark matter has a unique property. It can form ultra-dense cores. When fermions are compressed by gravity, they resist further compression through a quantum mechanical effect called degeneracy pressure. This is the same pressure that prevents white dwarf stars from collapsing and supports neutron stars against gravitational collapse. For fermionic dark matter, degeneracy pressure allows the formation of extremely compact and massive cores, far denser than ordinary matter but not collapsed into a black hole. Degeneracy pressure arises from the Pauli exclusion principle. When fermions are packed closely together, they are forced into higher energy states because no two fermions can occupy the same quantum state. This creates an outward pressure that opposes gravitational collapse. In white dwarfs, electron degeneracy pressure supports the star. In neutron stars, neutron degeneracy pressure provides support. In fermionic dark matter cores, the degeneracy pressure of dark matter fermions provides support. The key difference between a neutron star and a fermionic dark matter core is the mass scale. Neutron stars have masses between approximately 1.4 and 2.5 solar masses, with radii around 10 to 15 kilometers. They are supported by neutron degeneracy pressure up to a maximum mass called the Tolman-Oppenheimer-Volkoff limit, approximately 2 to 3 solar masses, depending on the equation of state. Above that limit, degeneracy pressure cannot resist gravity, and the neutron star collapses into a black hole. Fermionic dark matter, if it consists of lighter particles than neutrons, can support much larger masses. The maximum mass depends on the fermion mass and the strength of self-interactions. For certain parameter ranges, fermionic dark matter can form cores with masses of millions or even billions of solar masses, comparable to supermassive black holes, without collapsing. The radius of such a core would be small, comparable to the Schwarzschild radius of a black hole of the same mass, but the core would not have an event horizon. It would be a compact object supported by quantum degeneracy pressure. The fermionic dark matter model proposed by Crespi and colleagues has a two-part structure. At the center is a super-dense compact core with a radius of only a few light hours and a mass of approximately 4 million solar masses. Surrounding the core is a vast, diffuse halo, extending thousands of light years, containing additional dark matter with lower density. The core and halo are not separate objects. They are two regions of the same continuous dark matter distribution held together by self-gravity. Here's where it gets really strange. The dense core is so compact and massive that it can mimic the gravitational effects of a supermassive black hole. Stars orbiting the core experience the same gravitational acceleration as if they were orbiting a black hole of equal mass. The orbital dynamics, velocities, periods, ellipticity, are identical. S2's orbit would be exactly the same whether it is orbiting a black hole or a fermionic dark matter core. The study analyzed not only S stars but also G sources. G sources, also called G objects, are dust-enshrouded objects near the galactic center that emit thermal infrared radiation. Their nature is debated. Some astronomers believe they are gas clouds. Others propose they are binary stars surrounded by dusty envelopes. Regardless of their nature, G sources orbit close to Sgr A star, and their orbits can be used to constrain the mass distribution at the galactic center. Crespi and colleagues modeled the orbits of both S stars and G sources using the fermionic dark matter model. They found that the model reproduces the observed orbits as well as the black hole model. The statistical analysis showed that, with current data, it is not possible to decisively distinguish between the two scenarios. Both models fit the observations equally well. And the data showed something that simulations hinted at, but observations had not confirmed. The Gaia DR3 mission, operated by the European Space Agency, has mapped the positions and velocities of over 1.8 billion stars in the Milky Way. Among its many contributions is a precise measurement of the Milky Way's rotation curve, which shows how orbital velocity varies with distance from the galactic center. In the outer regions of the galaxy, thousands of light years from the center, Gaia observed a slowdown in orbital velocities, a pattern known as the Keplerian decline. The Keplerian decline is significant because it constrains the total mass distribution of the galaxy. If the galaxy's mass were concentrated entirely in the central bulge and disk, orbital velocities would drop off more steeply at large distances. If a massive dark matter halo extends far beyond the visible galaxy, velocities would remain high at large distances. The observed Keplerian decline indicates an intermediate case, a dark matter halo that extends outward but eventually tapers off. The fermionic dark matter model predicts exactly this behavior. The diffuse halo surrounding the dense core extends outward, contributing mass at intermediate distances. But the halo has a finite size. Beyond a certain radius, the halo's density drops sharply, leading to the Keplerian decline. In contrast, traditional cold dark matter models predict halos with extended power law tails that stretch to very large distances. The fermionic model produces a more compact halo with tighter outer edges. Crespi and colleagues found that their model matches the Gaia DR3 rotation curve when combined with the known mass of the Milky Way's disk and bulge. This is a key point. The model provides a unified explanation for both the inner stars near Sgr A star and the outer halo rotation. The black hole model requires two separate components: a supermassive black hole at the center, and a dark matter halo surrounding the galaxy. The fermionic model uses a single continuous dark matter structure to explain both. The difference between cold dark matter and fermionic dark matter halos is structural. Cold dark matter, often abbreviated CDM, is a theoretical framework in which dark matter particles are non-relativistic and collisionless. CDM halos form through hierarchical merging of smaller structures and follow a characteristic density profile called the Navarro-Frank-White profile, or NFW profile. This profile has a cuspy center with density increasing toward the core, and an outer region where density falls off as a power law proportional to 1 over radius squared. The power law tail extends to very large distances, meaning the halo has significant mass far from the galactic center. Fermionic dark matter halos have a different structure. The dense core at the center is supported by degeneracy pressure, producing a flat or declining density profile in the innermost region, not a cusp. The outer halo still decreases in density with distance, but the decrease is steeper than in CDM models, leading to a more compact halo. Beyond a certain radius, the halo's density drops off rapidly, producing the Keplerian decline observed by Gaia. This structural difference has observational consequences. If the Milky Way's dark matter halo follows the CDM NFW profile, the rotation curve should remain relatively flat at large distances, with velocities decreasing slowly. If the halo follows the fermionic model, the rotation curve should show a steeper decline at large distances, consistent with Gaia's observations. The Gaia DR3 data favor the fermionic model, though the difference is not yet conclusive. Dr. Carlos Arguelles, co-author of the study from the Institute of Astrophysics La Plata, stated, "This is the first time a dark matter model has successfully bridged these vastly different scales and various object orbits, including modern rotation curve and central stars data. We are not just replacing the black hole with a dark object. We are proposing that the supermassive central object and the galaxy's dark matter halo are two manifestations of the same continuous substance." But there's another problem that nobody expected. What about the Event Horizon Telescope image? If Sgr A is not a black hole, how can the fermionic dark matter model explain the shadow? The answer lies in general relativity. A black hole casts a shadow because light emitted near the event horizon is either absorbed by the black hole or bent into tightly curved orbits. The result is a dark region surrounded by a bright ring of light from hot orbiting gas. But a black hole is not the only object that can produce such a shadow. Any extremely compact and massive object that bends light sufficiently can create a similar effect. In 2024, a study by Pell and colleagues, also published in monthly notices of the Royal Astronomical Society, showed that a dense fermionic dark matter core, when surrounded by an accretion disk of hot gas, casts a shadow-like feature strikingly similar to the one imaged by the Event Horizon Telescope. The dark matter core bends light so strongly that photons emitted from the inner edge of the accretion disk are deflected away from the observer, creating a central darkness. The bright ring comes from photons emitted at slightly larger radii that escape and reach the telescope. The shadow of a fermionic dark matter core is not identical to a black hole shadow. The key difference involves photon rings, also called photon spheres. Near a black hole's event horizon, general relativity predicts that photons can orbit in circular paths before escaping or falling in. These orbits create multiple faint rings of light surrounding the central shadow. The primary ring is the brightest and easiest to observe. Secondary and tertiary photon rings are fainter and require extremely high resolution to detect. Photon rings are a signature of a singularity, the point of infinite density at the center of a black hole. A fermionic dark matter core does not have a singularity. The core has a finite density, supported by degeneracy pressure. Therefore, the fermionic model does not predict photon rings. If future observations with improved resolution detect secondary or tertiary photon rings around Sgr A, it would favor the black hole model. If no photon rings are detected, it would support the fermionic dark matter model. One group of researchers claimed in 2023 to have detected a photon ring around Sgr A using EHT data. However, that claim was heavily criticized by other scientists who argued that the analysis was flawed and the claimed detection was an artifact of data processing. As of 2026, the existence of photon rings around Sgr A remains unconfirmed. Now let's put everything together. Two models. Model 1, supermassive black hole. Sgr A is a black hole with a mass of approximately 4 million solar masses. It has an event horizon with a radius of approximately 12 million kilometers, about 17 times the radius of the Sun. Stars orbit the black hole due to its gravitational pull. The black hole is surrounded by an accretion disk of hot gas, which emits radiation across the electromagnetic spectrum. The Event Horizon Telescope imaged the shadow of the black hole, a dark region created by the event horizon. Photon rings may exist near the event horizon, but have not yet been conclusively detected. The black hole is distinct from the galaxy's dark matter halo, which extends thousands of light years and provides additional gravitational mass. Model 2. Fermionic Dark Matter Core. Sgr A star is a compact object composed of self-gravitating fermionic dark matter. The core has a mass of approximately 4 million solar masses and a radius of only a few light hours, comparable to the Schwarzschild radius of a black hole of the same mass. The core is supported by degeneracy pressure, preventing collapse into a black hole. Surrounding the core is a diffuse dark matter halo extending thousands of light years. The core and halo are two parts of the same continuous dark matter structure. Stars orbit the core due to its gravitational pull, producing the same orbital dynamics as a black hole. The core, when surrounded by an accretion disk, casts a shadow similar to a black hole shadow because it bends light strongly. However, the core does not produce photon rings because it does not have a singularity. Both models fit the current observations. The statistical analysis performed by Crespi and colleagues found that the fermionic dark matter model and the black hole model are equally consistent with the orbits of S stars and G sources. The fermionic model also explains the Gaia DR3 rotation curve, providing a unified framework for the galactic center and the galaxy's large-scale structure. We are not saying the black hole model is wrong. The evidence for a supermassive compact object at the galactic center is overwhelming. S2's orbit alone proves that something with approximately 4 million solar masses exists within a region smaller than Mercury's orbit. The Event Horizon Telescope image confirms that the object casts a shadow consistent with general relativity. The 2020 Nobel Prize was awarded for work that demonstrated the existence of this object. But the fermionic dark matter model is a viable alternative. It reproduces all the key observations: S-star orbits, G-source orbits, the shadow, and the rotation curve, and it offers a conceptual advantage. It unifies the galactic center and the dark matter halo into a single structure, rather than treating them as separate entities. Dr. Crespi noted, the outcome of these findings could potentially reshape our understanding of the fundamental nature of the cosmic behemoth at the heart of the Milky Way. And here's what this really means. We need better observations to distinguish between the two models. The key is photon rings. If secondary and tertiary photon rings are detected around Sgr A star, the black hole model is strongly favored. If no photon rings are detected despite improved resolution, the fermionic dark matter model becomes more plausible. Future observations will be decisive. The gravity interferometer on the Very Large Telescope in Chile is capable of tracking stellar motions near Sgr A star with extremely high precision. By measuring the orbits of additional SE stars and detecting subtle deviations from Keplerian motion, gravity may be able to distinguish between the black hole and dark matter models. The Event Horizon Telescope is also planning future observations with improved resolution, which could reveal photon rings if they exist. So what do we know for certain? A supermassive compact object with approximately 4 million solar masses exists at the center of the Milky Way. It is located at the position of Sagittarius A star. Stars orbit this object at speeds exceeding 2,000 kilometers per second. The object casts a shadow consistent with general relativity. The galaxy's rotation curve shows a Keplerian decline in the outer halo, indicating a finite dark matter distribution. What don't we know? Whether the compact object is a supermassive black hole or a dense fermionic dark matter core, whether photon rings exist near the object, whether the galactic center and the dark matter halo are separate entities or two manifestations of the same structure, and whether dark matter can form ultra-dense cores supported by degeneracy pressure, as predicted by the fermionic model. And here is the urgency. Improved observations with next-generation instruments are coming. The Event Horizon Telescope is upgrading its capabilities. The gravity interferometer is tracking more S-stars with higher precision. Within the next few years, we may have the data needed to distinguish between the black hole and dark matter models. Because if the fermionic dark matter model is correct, then the most studied supermassive compact object in the universe is not a black hole. It is a clump of dark matter, and our understanding of galaxy formation, black hole growth, and the role of dark matter in shaping galactic nuclei will need to be completely revised. The truth is this: we assumed Sgr A star is a black hole because no other known object can be that massive and that compact. But the fermionic dark matter model proposes a new type of object that can match a black hole's properties without being one. And until we detect photon rings or rule them out definitively, both models remain viable. And the only way to know which model is correct is to observe Sgr A star with the highest possible precision, search for photon rings, track more SE stars, and test the predictions of both models until the data force a conclusion. If this video changed how you think about the galactic center and the nature of supermassive compact objects, hit like and subscribe to this channel. We are tracking observations of Sagittarius A star as new data arrive from the Event Horizon Telescope and the Gravity Interferometer, and you will not want to miss what they reveal. Leave a comment with your prediction. Is Sgr A star a supermassive black hole or a fermionic dark matter core? And share this video with anyone who thinks we understand the center of the Milky Way. After this, they will realize we are still debating what kind of object controls our galaxy.